Okay, so I want to start this lecture by ending the previous lecture. And what I really want to just emphasize is kind of what you can do from this determinantal structure. Okay? And the idea is basically that you can do a lot of stuff by use of the methods of asymptotic analysis of integral formulas. So, but before that, let me just kind of start with something very basic. If you look at n choose k, okay, of course we know formula for this in terms of n factorial over k factorial n minus k factorial. And we know that by analyzing this, if you put a 2 to the minus n in front, you can compute the Gaussian density function and prove the central limit theorem, all that sort of stuff. And so one of the routes to considering asymptotics as n and k go to infinity is through Stirling's formula. Right? Everyone knows Stirling's formula. Does everyone know how to prove Stirling's formula? Maybe you've probably seen some proofs, but one of the proofs is through the gamma function and through asymptotics. But let me show you kind of a more direct route to studying asymptotics of n choose k. So if you write, of course, if we look at 1 plus z to the n, if we expand this, the coefficients are n choose k, right? We know this. But if we take a contour integral in the z variable, dz, and we divide through by z to the k plus 1, and I integrate over a contour that includes 0, maybe I choose it to be of radius 1 or whatever, and I divide by 2 pi I, then the Cauchy residue theorem tells me that this is an equality. Okay, so I don't know how much you remember complex analysis, but the basic idea is that when you integrate any sort of power, z to the r, around a circle, you get the indicator function, so dz, that r is equal to minus 1. I guess divide by 2 pi I. So just with this fact, you can prove this very easily. So what was the point of doing that? Well, the point is that if I want to now imagine, for instance, taking n choose, I don't know, n over 2 plus alpha square root of n, I can rewrite this in exactly the same way, and I get an expression. I'm not going to try to write it carefully, but I can write this in the form of e to the n and then some function of z, dz, where the n is coming both from this n and the fact that k is somehow proportional to n. Okay, maybe there's this and then an additional factor of the form e to the square root of n times some other function g of z. Okay. Now the point is that by studying this function that you get here, you can actually do asymptotics. You can find contours for which if you look at the critical points of this function, you can find contours where you localize this integral. So you basically will prove that the integral is very negligible away from a single point. And through that, you can prove asymptotics of this sort. So what you basically end up doing is you find the critical point. You find the z such that f prime of z is equal to 0. This represents in the complex plane a place where the level lines of the real part of the function f of x coincide. They look like an x. And you Taylor expand the function around that. The Taylor expansion balances this square root term. It gives you a quadratic term. And that quadratic term is what's giving you ultimately the Gaussian behavior of this. Okay, so there's this very simple, I'm not going to go through the detail, approach of asymptotic analysis that allows you to expand expressions of this sort once you have nice integral formulas. And the whole idea basically boils down to analyzing the function that comes up in the exponential as n goes to infinity. So whereas this looks more and more complicated as n goes to infinity, this type of expression somehow simplifies as n goes to infinity because it's only the critical points of this function f that matter. Okay? maybe I'll say one more word about the nature of this. So, the function, I'm not going to remember the details, but you basically find that there's a critical point. Maybe it's at +1 or something. And there's a behavior local to that, whereby if you take your contour to cross through the critical point, you can maneuver it so that the function decays rapidly away from the critical point. So this is the nature of whatever this function happens to be. You can check. And so if you deform your contour so that it crosses the critical point, you can then bound the integral as being negligible away from that, and you can localize the integral to this small window, in which case you can just Taylor expand, and you get basically a Gaussian type expression here. Okay? So that's the very basic principle of asymptotic analysis using contour integrals. Obviously, I could say much more about it, but with that in mind, let me just tell you kind of how you proceed from the type of determinantal structure that we arrived at in the previous lecture. Okay. So if you recall the idea, we had our Schur measure. Okay. And by way of this Cauchy bialternate formula and then this biorthogonal ensemble being a determinantal point process, we arrived at the fact that this is a determinantal point process. And moreover, using this bialternate formula and this expression for the kernel, in terms of that, we were able to write down, with a little bit of complex analysis that I'm not going to go into, the correlation functions. So I have my Schur measure. I'm going to assume m equals n just for the sake of what I'm going to write here. And I'll take all the AIs and all the BJs equal to some q in 0, 1. Okay? So in terms of the measure, I'm really looking at an m by m. And I'm looking basically at the last passage time where my geometric weights are q squared, in the notation I'm using right now. And so the Schur measure, which is a measure on partitions lambda, I write in terms of these coordinates, which I'll denote lambda I minus I plus a half. The half is kind of inconsequential. It just simplifies formulas slightly. So this is I equals 1 to n. And then the kernel that I get so this is an n point process, and its correlation functions are written in terms of this kernel that takes the form of a double contour integral with let me write it in the following form, I'm not going to do much with this, but I want you to see. So this is just rewriting what we had before. And then there's some expression, square root of VW. Where these integrals are occurring on a pair of contours, one a W contour that's included inside of a V contour, and both of which include Q and exclude Q inverse. So again, these are contour integrals. You should think of this as an iterated integral. So let's say you fix W as you fix a W and then you integrate V, and then you integrate that W of that resulting integral. And this function f encapsulates the, this is going to be defined as such. So log of 1 minus q over v minus log of 1 minus qv minus Well, it's just that. Okay. So this is the type of formula you get. And so what can we do with this? So the first thing that we can do is we can observe that the first correlation function, rho 1 of x, is just k of xx. So the first correlation function is a 1-by-1 determinant, so it's just the diagonal entry. And this is equal to the probability that x is in my point process. So in general, the one-point correlation function just gives you the empirical density of your point process. So in terms of the Schur measure, remember we had this picture where we were looking at, we had these sort of starting configuration, ending configuration for what the lambda is, the empty partition, and then we started kind of increasing and then decreasing. Eventually we kind of flatten out. And we looked at the intersection, and this was what this point process in question is, essentially. That's what this point process is. And so the question is, how do you transition from having density 1 to density 0 of the point process? And you get that by just looking at rho 1 of x. Now the claim is that when, for large n, the number of curves that will become active and the height of the maximal curve, we expect will deviate in a scale of order n. And so the natural thing to look at for this first correlation function is to actually look at rho 1 of, say, some constant u times n. Because this is going to say, kind of, as I vary in the scale of this limit shape, what will the density look like? And so when you do that, so maybe now let me look at this formula where I have u n un. So this is going to be the first correlation function. So then I get the same thing, except I don't need these terms anymore, but I can absorb the fact that x and y both are un and just change this function f by a factor of u log v. So this is giving me the first correlation function. It seems a little bit more complicated than my formula for binomial coefficients, but it's kind of a similar flavor, right? You have some large diverging n. You have something that looks like exponential of n times something, and then just some little thing that's not changing with n at all. Now, what's going to happen in this picture is the following. So you see I have this difference of the v and the w, and my v and my w live on different contours. So what I want to explain to you very briefly is how from this formula you can derive the limit shape, the analog of what you would call in random matrix theory the semicircle distribution. But of course here it's a slightly more complicated distribution. So what will this rho 1 un look like? So I claim it looks like the following. So there is some value of u. So this is going to be u. There will be some value of u for which afterwards the density, so I'm going to be plotting the density, this rho 1. Afterwards the density is 0. And there'll be some value afterwards the density is 1. Well, converging to 1 as n goes to infinity. And then there'll be some transition between it with some formula. And I'd like to know, first of all, where this is, and what this looks like. Okay? In other words, I want to know what this shape is. What's the limit shape? So let me tell you the answer, and then just give you a sense of how you get there. This function f, as before, the most important information about this function f is to understand the location of its critical points, because the location of the critical points are going to determine where, when we do various contour deformations using Cauchy's theorem, where we get the sort of main contribution to this integral. So the first thing that I do is I look at the solution to f prime equals 0. And I want to know what's the set of solutions to this. Okay, so I have my, you tell me what your favorite u is, maybe it's 0.7, and I say, okay, well, let me solve this equation. Of course, it depends on u. And we find that, in fact, there are always two solutions. So there's a v plus and a v minus. This is just because when you take the first root, you get a quadratic equation. And you see, in fact, that these v minus, they come in two flavors. Either they are complex conjugates of each other, or they're both real. So in the case where u is between, so let me put some numbers here. In the case where u is between 2q over 1 minus q and minus 2q over 1 plus q, so not complicated. In this region, you have v plus equals v minus conjugate. In other words, they are complex conjugates of each other, the solutions. So the critical points kind of will sit, in fact, they sit on a unit circle, but they'll sit complex conjugate to each other. And then in these other two regions, they will both be real. Okay? So in both of these and over here. In the region where they're complex conjugates, let me call, so they live, in fact, on a unit circle. And so I'll call v plus up here and v minus down here. And let me call the angle that's subtended between the x-axis and v plus, I'll call that phi. Okay. This curve is then given by phi over pi. So of course, phi is a function of u, because these v plus and these v minus, these critical points depend on u because f depends on u. And that's the limit shape. It's this angle subtended by these complex roots of this quadratic equation. Why in the world does this make any sense? Let me tell you a little bit more before I tell you why. In addition to this, you can show that outside of this interval, so what you should really have in mind, again, n is 1,000,000 now, and so what's really happening is I can imagine, I really want to look at a picture where the width is like of order n, but I've kind of compressed it to order 1. Let me imagine that, in fact, this is like u times n. So I've actually stretched out the picture. So in the bulk, what will happen is you'll have particles that are still living on the integer lattice, but they're kind of approaching this sort of fully packed configuration, right? So when they get to the when they get to the left of this point, minus 2q over 1 plus q, they basically join up with the integer lattice. And when they get to the right, they basically there are no points. And then in the middle, the density of points is transitioning. So you can also prove results that say that if you go, some positive constant times n to the right or to the left, that you have kind of an exponentially decaying probability of seeing any points. And here you have an exponential decaying probability of seeing any holes. You can also quantify locally, so if you zoom into an order 1 region in this bulk, you can quantify precisely what you see there in terms of another determinantal point process. So in the bulk, what you get is that, so in particular, if I look at un, let's say plus little x, and then un plus little y. So I'm looking at my kernel in a vicinity of position un, but then an order 1 window around that. That kernel, and hence the correlation functions, converges to something called the discrete sine kernel. Still, it depends on this same angle phi, so phi u, and then x minus y divided by pi x minus y. And this is if x is not equal to y, and if x is equal to y, it's just the, well, it's the diagonal term, which we already computed. So this is something that goes by the discrete sine kernel. If you look at the edge, then the density of particles starts to get more and more spread out. And in fact, the density, what will happen is you'll need to look in a window of order n to the 1/3 in order to see particles that have kind of a unit density. So the particles spread out by a scale n to the 1/3, and there you get a result of the following sort. So I'm going to look right in the vicinity of this edge times n, and then I look in some scale, there's some constant to get this right, n to the 1/3 x, and I do the same thing in the y coordinate. And this will converge. So first of all, the kernel is going to converge in this scale, but it's actually going to, the density is, right? The correlation functions are going to decay because the density is decaying. The density of particles is actually decaying like n to the minus 1/3 because you only have maybe 3 particles in a window of n to the 1/3. So first of all, this decays with like n to the minus 1/3, but then if you look at what's left over, you get convergence to something that's called the airy kernel. And this airy kernel, well, it's slightly more complicated than the sine kernel, but it's given again in terms of a double contour integral formula. Okay, let me write it actually in a simpler form as a single integral. So it's an integral of the airy function in x plus r and the airy function in y plus r. So this airy function, this is ai of x is what's called the airy function, okay, which can be written as the solution to a second order differential equation or in terms of some complex contour integrals. So I'm not going to use this beyond just telling you that the kernel itself in this scale has a limit, and what this ultimately translates to is the fact that if you look at the top line, let's say, and you look at the fluctuations of the top point, in other words, the last passage time, that this result here will translate into the fact that this last passage time, I think I called nn, will have some fluctuation. So first of all, the law of large numbers will tell me that it's like q over 2q over 1 minus q times n, right? So I need to subtract off, this is the top curve, I need to subtract off this number. And then if I scale by kappa n to the 1/3, I guess I should probably tell you what this kappa is. It's q to the 1/3, 1 plus q to the 1/3 over 1 minus q. Okay. That this will converge to some distribution that's written in terms of this k airy. Now, I'm not going to go through the details, but basically, if you have a determinantal point process and you have its kernel, you can extract what are called gap probabilities, the probability that there are no particles in a region or to the right of a region. And those end up being written in terms of infinite dimensional series of determinants that ultimately are known as Fredholm determinants. So you get a formula you get a formula for this in terms of certain determinants. And this is what's called in the literature the GUE Tracy-Whittem distribution. Okay, and all of that is coming from the convergence of the kernel in this scale to this airy kernel. Okay. Now, how does one actually, prove any of these things? And then I'll stop and go on to the material for this current lecture. It all comes down to the asymptotic analysis of this and the study of the critical point. So let me maybe just tell you about this picture. How do you prove this limit shape picture from these types of expressions? So the idea is that you look at your function f of v in Mathematica, and you look at the regions in which the real part of this function are positive versus negative, right? Because when you want to know the behavior of the exponential of something, if you can control the real part of the function, that's controlling somehow the modulus of the exponential, right? The imaginary part is just causing oscillations, right? Because e to the I is just an oscillatory thing. But the real part is controlling the magnitude of this expression. So if I look at my function, so what I'm going to imagine plotting now is something like the real part of f of v for v in the complex plane, okay? For different choices of u. So again, I have the choice of u, which is, let me call this thing, I don't know, u plus, and I'll call this thing u minus. Okay? So when u is bigger than u plus, what does this real part of f of v look like? Well, you can convince yourself that it looks like the following. And then what I'm drawing here are the level lines of this function real part equals 0. So along certain contours in the complex plane, the real part of my function f of v is 0. So in fact, on the contour that goes, on the unit circle that goes around 1, it's 0, and then there's 2 other contours around q and q inverse. And between that, in this region, it's positive. In this region, it's negative. It goes back and forth. It needs to, because of the nature of analytic functions. So look at this. We somehow want to move the contours in such a way as to minimize the oscillations, but also kind of control the behavior of this integral. And from what I've told you over here is we expect actually that this one-point correlation function, k, u, un, will be exponentially small when you're to the right of this u plus. So let me justify that. Okay, so there is a condition that the v contour be bigger than the w contour. This is because of otherwise I encounter a residue from v minus w. But you see the v contour wants to be sitting in the negative region. If I can get the v contour entirely in the negative region and the w contour entirely in the positive region, then the argument of the exponential will be strictly negative. And as I take n to infinity, I'll get exponential decay of the whole integral. And so luckily I can do that. I can draw my v contour. It needs to include the w contour, so I'll just deform my v contour so it sits entirely in this negative region. And I'll put my w contour entirely in the positive region. And when I do that, there's some maximal negative number and minimal positive number, but either way, those are strictly positive, or they're strictly away from 0. And so I get that the entire integrand is bounded by e to the some negative number times n. And I integrate over some finite contours. That doesn't change that. And so in so doing, I justify that this correlation function is exponentially decaying here. In fact, if you play a little harder, you can try to optimize, figure out exactly where you want to cross through, what point gives you the, what contour, say, for the v allows you to minimize the maximal negative part, and what contour for the w allows you to maximize the minimal positive part. And if you do that, you actually get the large deviation rate function for this top part, for this top. So that's what happens in this case. Now, the case where u is less than u minus, we expect actually that the first correlation function is converging to 1 maybe minus something that's exponentially decaying, right? Because we expect that it becomes essentially dense here, perfectly dense. So how do you, again, see this from the nature of this formula? So in that case, let me again draw what these level lines look like. So you have, again, obviously you need to justify that these are just drawings, so you need to justify that this is actually what happens. But so this is the type of level line that you end up seeing. These are all the 0 level lines of your function. And in this region, you have positive values of the real part. In this region, negative, negative, and positive. So again, what you'd like to do in order to get exponential decay is you'd like to put the v contour solidly in the negative region and the w contour solidly in the positive region, subject to the fact that they can't cross through poles at q, essential singularities at q and q inverse that come from these terms. And that, well, and then there's a simple pole coming from v minus w in the denominator here. And you see, however, that the regions are somehow out of order. V wants to include w, but here the positive region is on the outside in the negative region. So they've somehow switched their order. But this is a simple pole. And what you can do is you can, say, fix the w variable and deform the v contour to be smaller than the w contour. When you do that, you pick up a residue at v equals w. And when you pick up the residue, it just means that you need to substitute v equals w into everywhere else in the formula. Okay, so if you make that substitution, what you find is that this k u, un can be written as 1 minus the same type of integral, except where I've switched the order of the contours. So somehow the residue that you pick by crossing over this term just produces a factor of 1. Okay. Well, the reason for that is that okay. Anyway, this just comes from computing the residue in this expression, and so what you get is that the remaining integral can again be exponential, shown to be exponentially small, and that will justify the behavior in this region. When you're in between the two situations, so when you're in the situation where u is between u plus and u minus, the picture becomes slightly different. And what ultimately happens there is that your 0 contours, they end up intersecting at v plus and v minus. And then you have positive, negative as the signs. And so what you basically want to do, again, is you want to put the v contour strictly in the negative region, and you want to put the w contour strictly in the positive region. So what you'd like is your v contour should just cross through these little saddle points, and the w contour should cross through these saddle points. And that's great, except that this violates, at least on part of the region, it violates the ordering between v and the w contours. And so that means that between the angle v plus and v minus, you need to pick up a residue from this term. But again, that residue gives you a very simple integral, but it's an integral now on just part of a curve. In fact, what the integral ends up being is it's the integral of 1 over v, 1 over 2 pi I between v plus and v minus on this part of the curve, so dv. But this is exactly equal to this is exactly equal to the angle divided by pi. So this is that's the angle of this arc. And that's what proves this formula. And then when you want to go beyond that, you get to get to this formula, you use the fact that, well, if I wasn't exactly looking on the diagonal, if I added plus x and plus y back into the picture, I would get something like v to the x, w to the minus y. And if you stick that type of thing in here, you end up getting integral expressions for this sine function. Okay, so the point of all of this is to say that using these determinantal methods, you can extract the asymptotic behavior of the top curve as well as the entire ensemble. With a little bit more work, you can extract this multi-point asymptotic. So you can take any finite number of slices, let's say k different slices, and you can write down that now you have a collection of point processes. You can think of these point processes as being indexed by which of these slices they live on and then a location, right? So you have, rather than z as your index set, you have something like, the numbers 1 through k and z as index. And now you can write correlation functions. And again, they take a very similar form using very similar methods of determinantal calculus. And you can, from that, derive multi-point asymptotics. In particular, you can prove results about not just looking at a single point of last passage percolation, but multi-point asymptotics. And I'll tell you the nature of those results in a little while. But the thing that I want to turn to now is the following perspective, the following idea. So when you look at this picture, somehow there are two orthogonal perspectives that we've presented so far. One perspective is that of what I just talked about, which is I slice it at a few locations and I look at point processes. And I want to say, how do these point processes converge as n goes to infinity, or I scale the locations of where I'm focusing. But somehow that perspective forgets about the fact that these were curves, or non-intersecting geometric random walks. And so the convergence, and the nature of convergence should not just be restricted to slicing at a few times. That's like saying, you have a random walk, it converges to Brownian motion in the sense that at any finite number of times it converges to a Gaussian process with some joint correlation. What is a more powerful perspective is to say that the entire process, the entire collection of curves, converges. And moreover, to say that the limit that you get, or the limits, depending on where you're focusing your attention, inherit the Gibbs property that is coming from the nature of the definition of the Schur process. And so what I want to describe in the rest of this lecture is, well, first of all, what is the nature of that Gibbs property? I've alluded to it, but I want to be more concrete. And then what are the tools in showing not just these finite dimensional convergences that determinantal calculus gives us, but actually functional convergences, and how this Gibbs property kind of plays well in that perspective, how that can be used to extract functional limit theorems. Any questions before I erase some stuff? Yeah?
Yeah. A Gaussian process is determined by its correlation function.
Yeah.
And it's tempting, because the name here is kernel,
Mm-hmm.
it's tempting to try to create a bridge between these two ideas. Does it have an idea like that?
Well, yeah, so first of all, for a determinantal point process, it is again determined by its correlation kernel in the same way that a Gaussian process is determined by its covariance matrix. So that already is a similarity. If we're talking about the sort of multi-point thing, then there's what you would call an extended kernel, something that involves not just the locations on a single slice, but also keeping track of, I'm looking at what's the probability that a curve passes through this point on this slice, and this point on this slice, and this point on this slice. It's a more general notion. But again, it can be encapsulated by these types of kernels. The challenge is, so for a Gaussian process, you can prove, obviously, that you can, well, actually, for any process, right, if you know the sort of finite dimensional distributions, you can show whether or not there exists a continuous modification of your process. And here you would hope to do the same thing, right? You have some sort of finite dimensional information. You'd like to say, well, okay, so there exists a continuous version I know this for any k slices at any k locations for arbitrary, for arbitrary k. But it's a little bit more complicated because it's not a single function that's being described, but it's a collection of points that's being described. So there's considerable more work needed to even establish from this determinantal structure that there exists a continuous version of the type of scaling limits that you get if you look at the collection of curves, say, at the edge, as n goes to infinity in a certain scale. But moreover, it's very hard. You can do it, and in fact, we have a perspective that explains this, but it's not obvious at all from the determinantal type of structure how to translate that back into this Gibbs perspective. So there is a translation that works very well at the finite level, but doing that in the continuum, it can be done, but it is not nearly as transparent. So. All right, other questions? Yep.
How do you see the n to the 1/3 from the contour expression?
Yeah, that's a great question. So the n to the 1/3, just very briefly, happens because so as I said here, you look at your critical points. So the critical points are v plus and v minus. This is when you're strictly inside. As u approaches the two boundaries, let's say as you approach this positive, u plus, these critical points, the angle, as kind of indicated by the way I drew the curve, the angle shrinks. And so these two critical points, these two quadratic critical points, join together. And when they join together, they create a cubic critical point. Okay? So what you end up with is a picture where you have, so you no longer, you're basically locally coming in at some angle. Each of these angles is 60 degrees. So there's also a zero path so that you have kind of three, they're not circles, sorry. So you have this sort of triple point that occurs. And when you do that, what will happen is in this exponential, so we're focusing around a critical point. So the 0th order terms will cancel at the critical point just because you have v of w minus f of v minus f of w. So at that critical point, the 0th order terms cancel. Since it's a critical point, the first order terms are both 0. And since it's this a cubic point, then in fact also the second order terms will cancel. So the first non-trivial term in the Taylor expansion at that critical point is a cubic term. So you end up with something that really looks like n and then f, so behaves like v cubed and w behaves like w cubed. And so the n to the 1/3 comes from the fact that if I want to absorb this n into the v and the w, I absorb it as n to the 1/3. And so all of the sort of expansions and all of what's left over comes from this cubic behavior at that critical point. Okay? And that's from the merging of these simple critical points. Okay, but again, there's much to be said about these asymptotics that I'm not going to say. So what do I want to say now is I want to go and talk a little bit about this Gibbs perspective, this Gibbsian line ensemble perspective, and how it complements the information that you get from determinantal methods, and how it leads to a sort of richer asymptotic picture than just that of looking at the scaling limits of determinantal point processes at finitely many slices. Okay, so let's kind of back up a little bit now. Let's remember our Schur process. So the way the Schur process worked was I chose a downright path. Let me choose a path that kind of goes to the right pretty far and then down. Okay? And then at each vertex, I had a partition. Okay? and I labeled them lambda 1, lambda 2, lambda 3, so on and so forth. Now, here's an observation. If I look at the law of lambda 1, lambda 2, lambda 3, so on and so forth, it doesn't actually depend on the path gamma as long as the path gamma includes these particular points. So the law, the marginal law of, say, lambda 1, lambda 2, lambda 3, lambda 4 is the same for this gamma as it would be for this gamma. And that's not immediately obvious, right? Because, again, for different gammas, remember I have this description of the joint distribution of all of these partitions indexed by the trajectory of the downright path as the product of these skew-Schur polynomials, with some normalization. So why is it that they have the same marginal as long as the paths coincide is because I can, when I do the integration out, when I sum out over, I keep summing out these different values, eventually, in either case, I get back to a Schur process that looks like this. So I kind of integrate everything else out, and I get back to the Schur process that has just this square downright path. And so the laws, of course, then of this side will coincide regardless of what the rest of the trajectory is. So with that in mind, I can even consider, for instance, a trajectory that goes arbitrarily far. So I can really think of my lambdas as living on a gamma that just extends horizontally infinitely far. Okay? And when I do that, I can say that the law, so the probability distribution under this Schur measure of the first k points, lambda 1 through lambda k, is given, well, it's given by these s lambda 1 a1, s lambda 2 over lambda 1 a2, up to s lambda k over k minus 1 ak, and then by this integrating out, I get left over s lambda k. Now the Schur process, the Schur polynomial in variables b1 through bn. Okay, so I'm assuming I have my b1 up to bn, and then a1, a2, and so on and so forth. Okay. With a little bit of thought, you can see that in fact this tells you that the lambda process, if I think of this as a process in the horizontal component, in the horizontal coordinate, that this lambda process is a Markov process on partitions. So the probability of a given lambda k plus 1, given my knowledge of all of the lambdas from lambda 1 up to lambda k, is given by just using Bayes' rule, lambda k plus 1 over lambda k in the variable ak plus 1, and then what's called a dupe H transform. So s lambda k plus 1 in the vector b over s lambda k in the vector b. So the idea is the following. If I know the history of my Markov process on partitions up to time k, the transition probability to the k plus 1 state only depends on the state lambda k, and it's basically given by taking a skew-Schur polynomial between lambda k plus 1 and lambda k, which I'll remind you is the indicator function that lambda k plus 1 interlaces with lambda k times a k plus 1 to this difference of sizes. And then there's this conjugation. And so what's really going on, what you should really have in mind is the following picture. So I can I do my usual plot of the lambda. So here's lambda k. maybe I apply the shift so that I separate points out. But anyway, so I have some partition. And what I want to think of this as doing is, well, if I didn't have the indicator function, what would be happening is each one of these, so lambda k sub 1, each one of these would take a geometric step with perimeter ak plus 1. And then this would become lambda 1 k plus 1. And this one would take a geometric step, and so on and so forth. But I have the indicator function. So the indicator function kills me if my random walks intersect each other. And so I get, rather than a Markov transition, well, OK, almost, there needs to be some normalization. But rather than a Markov transition probability, I get a sub-Markov transition probability. Right? Because I'm basically taking n random walkers with geometric jumps, and I'm killing them if they ever touch each other. So it's a sub-Markov transition probability. The purpose of what's going on here, this conjugation, is to make this, and you can prove that this is in fact a probability based on the Cauchy identity, is to turn this back into a probability distribution. And that's the distribution that comes just by using Bayes' rule from this formula. So how should we think of this? What you should really think of this Dupage transform as doing is it's taking independent geometric random walks with these maybe with these inhomogeneous jump rates, A1, A2, A3, so on and so forth, and it's conditioning them at infinity on having certain slopes. And in fact, having slopes in such a way that they kind of get separated out. So one way of interpreting this Markov chain is to consider, up to some very, very large time, consider these geometric random walks, condition them to not intersect by taking them to go kind of asymptotically to certain slopes, and then to take that to infinity. And this is another way of producing the same Markov chain. If you've ever seen Dyson-Brownian motion, this is essentially a discrete analog of Dyson-Brownian motion. Dyson-Brownian motion is what you get by taking Brownian motions from some particular starting points and conditioning them to never intersect up to time infinity. And you can, of course, create Dyson-Brownian motions with drifts by conditioning them to go off at different slopes. Of course, you want the slopes to somehow be spread out so that that's a non-trivial conditioning. OK, so this is one perspective already on how to think of this. And you see from this perspective that you really have something like these independent random walkers conditioned on non-intersection between them. And so we'd like to kind of expand on this notion. So if I look at this Markov chain, if I look at this process that I have along gamma, I can ask, let me slice it at two different times, so S and T. And I'm going to ask about what is the law of my partitions inside given everything exterior to it. So I have all of my lambdas before. Here's lambda T, here's lambda S, and so on and so forth. What is the law of these lambdas conditioned on everything external to it? But of course, because this is a Markov chain, because we have this nice description, we can write this down, and we see that the law of the collection internal to this interval, so lambda s plus 1 to lambda t minus 1, given all of the lambda k for k not in the interval s plus 1 t minus 1, is actually proportional to what? Well, first of all, it only depends on the value of lambda s and the value of lambda t. You can see that directly from this type of expression. And it's proportional to the product of the s lambda k plus 1 over lambda k ak plus 1 for k between s and t minus 1. In other words, if I have this long product of these skew-sure polynomials, if I condition on all of the values up to, except for some region, and I want to know what's the law inside, well, Bayes' rule gives it, and it just says that it's proportional to the product of these things, but given the boundary terms lambda s and lambda t. So this is this is the Gibbs property. Okay. But there's an even stronger version of this Gibbs property, which is that, remember these lambdas, these are partitions, okay? So, and remember the S lambda over mu takes this form, the indicator function for interlacing. But the indicator function for interlacing is really a local condition. So let me, kind of hearkening back to the beginning of the first 2 lectures, let me rewrite what this Gibbs property looks like in terms of these now n-layer Gibbs measures. So I can write this type of measure in the following way. So let me draw n layers. Okay, so on and so forth. And maybe I'll do one more layer. And the rule is, so I have these 2 types of edges. There's no boundary condition edges. There's no dinosaurs or boots. Okay. And so here I have my lambda S1, lambda S2, and lambda Sn. And then here are my lambda t's. And every other point inside of here is labeled. So all this first, the vertices here are labeled by the value of the partition. So I think of this as a graph, and I'm putting a configuration on it. So I'm just putting a collection of non-negative, of non-negative integers along this. So this would be lambda 1 s plus 1, lambda 1 s plus 2. This would be lambda 2 s plus 1, so on and so forth. And the weight that I get by just using this expression for sure polynomials is that every diagonal, so if I go from a value x to y, the weight of this, and I always have so this I have an a s plus 1 and a s plus 1, so on and so forth, a s plus 2. These are these edge parameters. So this is the indicator function that y is bigger than or equal to x, a to the y minus x. And the weight of these diagonal is just the indicator function that y is bigger than or equal to x. So this picture, this n-layer graph, is actually precisely the same as this measure here, this Gibbs measure here. Just because the interlacing condition is enforced by the indicator functions that you see here, right? So this interlaces with this, which interlaces with this, which interlaces with this, and so on. So the zigzag is exactly the interlacing. And then the a to the difference in the size, well, you factorize this into the difference of the first coordinate, second coordinate, third coordinate, and so on and so forth. And so now you see actually that the Gibbs property, there's a stronger version of it, which is not only, do you say, let's say, condition on this entire partition and this entire partition, but imagine that I wanted to know just the law of the top curve given everything exterior to it in the entire line ensemble. Of course, the thing continues in this direction and continues in this direction. This is really somehow a semi-infinite Gibbs measure. Well, the Gibbs measure it's a local Gibbs measure. So the law of the configuration at these 4 points only depends on the configuration at the points that are immediately exterior to it. And so this gives you even a much nicer perspective on what this Gibbs property is, which is to say that, it's like the Gibbs property for tiling models, for the easing model. It extends to this much more local. You don't need to look partition by partition, but you can go part by part of the partition. Okay, so this is a nice perspective, but the perspective that somehow is the most valuable for my purpose is to think of the law of the lambdas along each of one of these diagonal lines as being the law of independent geometric random walks. And then to think of these dotted lines as creating an interaction between these random walks. So if I want to know the law of lambda 1 between s plus 1 and say t minus 1, conditioned on everything else, I should really think of it as a geometric random walk, maybe inhomogeneous jump parameters, conditioned on starting at a certain value, lambda 1s, ending at a certain value, lambda 1t, and not intersecting with the curve lambda 2 that sits beneath it. Now, why is this a valuable perspective? Well, if you think of your, so if I kind of imagine plotting out now the lambdas in maybe I do this, I do the sort of graph that I was talking about before, where we plot out each, you do some shift and you start plotting out the trajectory of the lambdas, so on and so forth. So what you see is that the results that we proved in the previous lecture, but the results about the determinantal point processes tell me that if I go, say, distance n, the gap between the first two curves will be of order n to the 1/3. This is the nature of the type of asymptotic results that we saw. And so if the gap between the first two curves ends up at distance n being of order n to the 1/3, and similarly that is the order of the gap of the first few curves, it gets tighter and tighter as you go deeper in, then the fact that you have this local geometric random walk Gibbs property is suggesting that as long as you look transversally in a scale which is of order n to the 2/3, your random walkers will not really interact too much. Right? The typical spacing, so they'll behave basically on a scale of n to the 1/3 and then transversely n to the 2/3. They'll behave like Brownian motions conditioned on non-intersection, right? Because random walks, when you scale by, when you scale on a large diffusive scale, converge to Brownian motions. So with this in mind, let me state a theorem. Okay? So the theorem now combines this perspective that you have this local Gibbs property and also our earlier determinantal structure result, and it tells you exactly what you should see as the scaling limit at the edge of your Schur process. All right, so as before, we're going to fix AIs and BJs identically equal to, let's say, Q. And we're going to consider fixing that there's, you have B1 through Bn. Okay, so, really, I want to imagine a picture where I have kind of a very long, large height, and then a very large width, something that's of order n. Okay, and I'm looking at a sort of LPP on that picture. Well, I'm really looking at the Schur process on that picture, but maybe I'm even looking the Schur process that kind of keeps going infinitely far, but I'm looking in the vicinity of something of order n. So I look at the Schur process on this horizontal path gamma. I get my measure on the lambda 1, lambda 2, so on and so forth. And then I define something I'll call ln k of t. Now this n is somehow keeping track of the scaling parameter. And this is going to be, I look at the kth curve, so lambda sub k, and I look at the horizontal location, which is like n plus something that's of order n to the 1/3. So there are some constants. So there are explicit constants. I'm not going to try to write them down. So such that we already know what some of these constants are. If I look at, so I'm basically looking around the horizontal component, that coordinate that's n, plus a deviation of order n to the 2/3. So that was the thing I was just kind of indicating, is indicated by this Gibbs property. And then I subtract off C2 times n. So I know what C2 is. It was this 2q over 1 minus q that we had calculated before. So this is the law of large numbers. And then I subtract off another thing times n to the 2/3. This is because when I look at my collection of curves, there is some sort of overall slope. So I need to look at the local slope of it and remove it on that n to the 2/3 scale. And then divide through by order n to the 1/3. The claim is that this, the process, kt maps to ln kt, converges weakly. So in the local uniform topology, as n goes to infinity, to a continuous process, kt maps to, I'll call this L, kt, which is called the parabolic airy line ensemble. And this parabolic airy line ensemble, I'm not going to write this down, but this is if you look at LK, let's say T1 up to LK, I don't know, TR for K, well, I'll tell you about this in a moment. So first let me parse the theorem. So what the theorem is saying, again, is that I look at the top, so that the nature of this convergence, the topology that I'm working with, is one that really focuses on the convergence on compact windows of K and compact windows of T, the uniform convergence of these functions, these random functions, to some limit. So what you should really imagine is you have kind of in this vicinity of n, and for n curves, you have some fluctuations, and you're looking in this n to the 2/3 transversal window, and you're scaling by n to the 1/3, and you're seeing that these fluctuations will converge locally to some collection of curves. And that's what these LKTs are. And moreover, these LKTs are, if you look at their finite, if you look at where they intersect a finitely many number of vertical curves, what you get are determinantal point processes. So if I looked at a single slice, I would get this point process with this airy kernel I'd written down. And if I look at multiple slices, I'll get some extended version of that. So this is this parabolic airy line ensemble. And moreover, this parabolic airy line ensemble enjoys, because of this property for the pre-limiting model, it enjoys a version of this Gibbs property. So let me describe what this Gibbs property becomes in the limit. So let me try to draw the kind of the big picture a little bit better. So again, so the picture to have in mind, so you have your initial your discrete model, and you have all these geometric random walkers conditioned on non-intersection, and you kind of do that, and they get denser and denser because they're kind of being forced together. And what's happening is that eventually they kind of are forced to stay put. Okay. So we somehow proved that there was already some sort of limit shape whereby they kind of stay put outside of that. And we proved that there was some limit shape on the top. And what we're doing is we're zooming in. So we've kind of chosen n so that n of these are being perturbed, and we're at distance roughly n. And we're drawing a box, a sort of, well, really a rhombus, that's of height n to the 1/3 around this limit shape, transversal n to the 2/3, and we're observing what happens within this box of these curves. And of course, in this large box, these curves start to look like Brownian motions. And so in the limit, as n goes to infinity, you get this picture of these non-intersecting Brownian motions. They actually have a sort of parabolic decay. This has to do with the fact that there's curvature of the limit shape that's not being captured in the scaling and the centering of this LK. I'm only centering it by a linear term. So there's some overall curvature of the limit shape. And that's the top curve, I would call it this L1, second curve L2, third curve L3, so on and so forth. They're non-intersecting because, well, they started non-intersecting. Okay, and you took a limit. Now, a priori, they could in the limit intersect because I'm scaling my spacing by n to the 1/3, right? But we know from the 1-point information that at a given slice, there's kind of typically an n to the 1/3 gap between these levels. And so the Gibbs property actually allows you to propagate that and say, well, that actually means that on entire intervals of width n to the 2/3, the likelihood that they come close in this scale is small. So that in turn allows you to show that if you know finite dimensional distributions, the wiggles of these curves are basically the wiggles of Brownian motion. So there is tightness in this sort of functional sense. And that's how you really prove this type of result. The Gibbs property is also inherited by the limit, and it's a very simple Gibbs property. So let's say that you fix some now macroscopic times s and t, and maybe you fix a level, say, k1 down to k2. What the Gibbs property tells me is that if I know the values of my curves k1 through k2 at times s and t, the law of what, and I know the curve beneath it, so I know the value of this, and I know the value of this curve, then the law of what sits in between is exactly that of three Brownian motions three Brownian bridges conditioned to start at these points, end at these points, and not intersect with the curve beneath it or above it. So the law is invariant under the action of erasing what you have here. And then, well, one way to proceed is to just have a bag full of Brownian bridges and just start to put your Brownian bridges in. And you say, oh, does this one work? And the answer is no, because these intersect. And so then you throw out these Brownian bridges and you sample again. Do these Brownian bridges work? And the answer is no, they intersect with the bottom curve. And eventually, if you keep kind of sampling Brownian bridges in this way, this sort of rejection sampling method, you'll end up with a candidate Brownian bridge triple that works, and that will be the original measure. Okay, so that's the nature of the Gibbs measure that you get in the limit. Okay, so this Gibbs property is very useful. In particular, you see it allows you to extend information from kind of finite dimensional times to spatial times. So this allows you to, say, control wiggles, to control interactions between multiple curves. It also lets you control, for instance, the behavior of erratic behavior, the occurrence of erratic behaviors, like the first curve jumping very high at random points. So what I want to do in the last, I don't know, 10 minutes or so is just give you kind of the one fundamental property tool about dealing with these Gibbsian line ensembles, which is used all over the place, which is called stochastic monotonicity. Okay, and of course, this is a much more general concept that applies in lots of different cases, so not just to these models that I'm talking about. So what is the idea here? Well, let me start with something very basic. If you have a Brownian motion, or let's say a Brownian bridge even, if I have a Brownian bridge, say from 0 to height x, and then I have a Brownian bridge from 0 to height y, here maybe y is bigger than x. A priori, if they're independent, there's no ordering between them. All right. On the other hand, it seems kind of clear that the thing that goes to the higher point should somehow be above the thing that goes to the lower point, right? In the sense that, well, even if I just look at the intermediate time, I know that in intermediate I have two different Gaussians, and one Gaussian has a higher mean than the other Gaussian. And so you should be able to somehow couple, maybe at an intermediate time, at a given intermediate time, the distributions in such a way that they're ordered. But of course, you should be able to do that in a functional sense as well. Now, for the Brownian bridge, this is extremely easy to do, because a Brownian bridge under an affine transformation becomes a new Brownian bridge. So if I take if I have in my pocket a Brownian bridge from 0 to 0, if I simply add in the function x times t, let me think of t as my horizontal variable, then I will produce out of this a Brownian bridge that goes up to height x at time 1. But of course, this affine shift, maybe I should draw it on top, this affine shift will respect ordering. Okay, I'm not doing a very good job of drawing it, but it will respect the ordering. And so in this way, I can actually couple together every single Brownian bridge in the whole universe, based on the ending points, all of the Brownian bridge measures. I can couple them together in a grand coupling, meaning that they're all coupled to the same probability space in such a way that if the endpoint is higher than the endpoint of another, the paths themselves are entirely above that of the other. Okay. So this is great because you have this nice affine property. Of course, you can ask whether you have such properties true for more discrete objects. So for instance, if you look at simple symmetric random walks, or maybe more relevant for us, if you look at geometric random walks, I can condition, say, a geometric random walk to end up at a given height, and I can condition it to end up at a higher height. And you can ask, well, is it possible to couple them together in such a way that, maybe I should do that earlier, in such a way that they stay ordered for the entire trajectory? So who thinks that you can do this now for geometric random walks? Is this a property that's very special to Brownian motion, or is this something that's kind of a little bit more general? So who thinks that you can do this for, well, first of all, who understands what I'm saying? Okay. Who thinks that you can do this for geometric random walks or bridges? Okay. Who thinks you can't do it? Okay. Who thinks? No, so you can do this. In fact, you can do even stronger things. So let me tell you kind of a stronger thing that you can do. I won't state a precise theorem, but you see it in the notes. So imagine that you have some set of starting points, I don't know, x1 through xk, and some set of ending points, y1 through yk, and you have some width. And maybe you even have some function that sits beneath you and some function that sits above you. So some function f and some function g. And of course, you need these functions to be, and the starting and ending points to be such that there exists, let's talk about geometric random walks, that there exist some geometric random walks that will realize paths that will stay ordered, strictly ordered in between and not intersect the f and the g, right? You know, kind of the similar idea as what was over here. So if you have such admissible boundary data, you can define the conditioned, you can define a measure which is that of random walk, geometric random walks conditioned to start and end at these x and the y points and stay between f and g and never intersect. Okay, so you know you get such an, you know, you have such an instance of this. I'm not going to try to draw it very precisely. So this is one instance of that. Now what you can do is you could imagine taking these numbers and shifting them up. And taking f and g and shifting them up. Well, the natural guess is that if you do that, the probability measure can be coupled in such a way to stay above the initial probability measure. Somehow, if the boundary data is lifted, then the measure is lifted, in the sense that there exists a single probability space on which you have that almost surely the sample of under the original measure is beneath that under the new measure. Is it clear what the statement is? So I have two measures. Let's say a priori I have a white probability measure, which is the thing I described, and a pink or red probability measure. And I want to basically show that there is some stochastic monotonicity. And what that really means is that there exists some overall probability space, I'll call P tilde, on which you have two sets. So maybe I call these the L's, and then the red things, the resulting red things, I call L, well, red L. So I have a probability measure on the vector on the paths L and the paths L prime, under which, so such that the probability that this is true in a kind of functional sense, so for every point and every height that this is true, is 1. And moreover, if I look marginally at L, this is the P of L, and if I look marginally at the other path, this is the P of the other path. Okay, is this clear? Yep.
The shifting you're talking about is not homogeneous.
No. Well, okay, obviously if I added a million to everything, then yes, it's obvious. But no, it could be simply something like I take my G and I move it to infinity. So I remove the barrier on top. And you know, it makes sense, right? If somebody is holding you down, if you lift that, you expect the whole curve set to move up. Or, you know, analogously in the other direction, if something's pushing you up from below and you move it down, you expect the whole system to drop. And this is the type of monotonicity that allows a lot of the types of arguments that occur in this study of these Gibbsian line ensembles to go through, because it allows you to reduce a lot of considerations to just questions about Brownian bridges or random walk bridges or non-intersecting. So there are two things I could do, and maybe I'll just do one of them, which is to tell you one way to prove such a result. Okay. Well, there are many ways. So one way to do it is to actually exhibit such a probability space, basically write down a bunch of uniform random variables and kind of couple everything to uniform random variables and do this all by hand. But there's a simpler conceptual way, which is using Monte Carlo Markov chains. Okay? And the idea here is really just the following. So imagine starting, you know, because I have this ordering, it should be clear that there exists at least one state in the white, you know, that's admissible for the white boundary condition that sits below a state admissible for the red boundary condition. So let's accept that that's true. Now, if that's true, now let me imagine starting a Markov chain. So the state space of my Markov chain is on path configurations. Okay? And the Markov chain, what I'm going to do is I'm going to have a coupled Markov chain. So I have so I think of some starting, so again, I call LVEC the entire trajectory of these, let's say, k curves, and I think of this as being indexed by some time t. So I start with this being less than or equal to the coupled thing at time 0. Okay, so you believe that you can do this. You can find states with the correct boundary conditions that satisfy this. So let's accept that that's true. And now how do I evolve these? I'm going to evolve these in time coupled to the same randomness, and I want that the coupling preserves the ordering. Moreover, I want that this coupling, as t goes to infinity, will converge to a stationary measure in both of these, and I want the stationary measure to be the Gibbs measure that I'm interested in, this conditioned random walk measure. And so how do you do this? Well, it's very simple, in fact. What you do is the following. So at each time, let's say it's discrete time, at each time you choose a coordinate, a horizontal coordinate. And at each time you choose a vertical label, 1 through k. And at each time you choose a number plus or minus 1. So there's this, at each time you choose a horizontal coordinate. Okay, maybe I should use tau instead of t for this time here. So, because I was using t for the horizontal. So I choose a t, a horizontal coordinate. I choose a number I between 1 and k, and then I choose some Bernoulli in the set minus 1, 1. And what I do is I attempt to change the ith curve at position, horizontal position t. I try to change the value. Let's say that it looks like this locally. I try to change the value there by adding plus 1 to it, or minus 1, depending on which thing I had there. Now, I don't just do that. What I do is I look at the probability under this measure that I'm looking for, this limiting conditioned measure. I look at the probability of the new configuration versus the old configuration. And I compare the ratio of, let me call L prime, which is the proposed new state, to the probability of having seen the state that I'm currently in. So I'm at time tau. And I compare this to a uniform random variable. And if it's less than a uniform, so I sample a uniform random variable. If it's less than that, then I accept the move. If it's bigger than it, then I don't accept the move, and I stay in state L, not L prime. And I do the same thing for the same u. So the u's are the same, so these are on the same probability space. For the proposed state of the red Markov chain. And I compare that also to the u. And I accept it if it's less than the u, and I reject it if it's not. So first of all, there's the claim that doing this procedure and comparing to the same u maintains the stochastic ordering. So it maintains the fact, it maintains this fact. And the reason why that's true is that the underlying random walk measure can be written for a geometric random walk. It can be written, so if I have a geometric random walk between 2 points, x and y, the measure can be written in the form of e to the sum, so let me say, the path is L, of L of, the form of h of L of s minus L of s minus, or something like that, maybe s plus 1 minus L of s, s equals, 0 to t, where h is convex. So there is a general class of random walks where you have some energy that you think of as giving you the sort of local, well, in fact, this is like the local Gibbs, this is the Gibbs weight takes this form of e to a convex function, which of course is going to be true if you just write down what this condition is for geometric random walks. And the convexity of this h implies that if this inequality holds, this one must have held as well. So basically, these ratios are ordered. So this ratio is, I guess, less than this ratio. If the L's are initially ordered, then this preservation of ratios will preserve, which will mean that the jumps will only occur in such a way as to preserve the ordering subsequently. Okay? So that the convexity comes from comparing this type of term to this type of term. There's 4 terms, you cross multiply, and you see that it all boils down to the convexity of H. So in fact, this is a much more general statement. It depends just on H being convex. Well, once you've done that, you're basically there, because you then note that, well, what I did was just describe a Monte Carlo Markov chain for sampling P, or P tilde. Right? The nature, this prescription of how to run these dynamics will converge as t goes to infinity to these stationary measures. And since they're ordered for all times, the stationary measures need to be ordered in this stochastic way. So that proves this monotonicity. And with this monotonicity, you can prove all sorts of wonderful things. You can, for instance, show that the top curve can't kind of jump spuriously high at random points, because you can somehow reduce the considerations of the top curve to the considerations of Brownian motion or Brownian bridges, and Brownian bridges don't do that type of thing. So I think I should stop and just quickly summarize. So we were basically kind of come to the close of the cycle on these Schur processes. I'll talk a little bit more about them in the afternoon from the perspective of the RSK correspondence. But in a sense, what we did is we started with these 2-layer Gibbs measures. Then we put this in the context of these general Schur processes, these n-layer, multi-layer Gibbs processes. We connected this to determinantal structures, and that gave us some finite dimensional information. And then we connected this to these Gibbsian line ensembles that allowed us to extract continuous scaling limits that enjoy these nice Gibbs properties. And this gives us a very nice characterization of some sort of universal continuum object. So in the next lecture, I'll even give you a little bit more information that says that these line ensembles contain not just information about the kind of origin to a certain endpoint last passage times, but actually kind of arbitrary starting to arbitrary ending point last passage times. And so really they contain the sort of full information of what last passage percolation behaves like. And then we'll go from there. All right, thank you.